Okay, so let's continue from where we stopped. So yeah, I was asking about inertia. Anyone heard about inertia before? Okay, okay. Let's jump straight into it. So power system. So in inertia, in terms of power system, can you all hear me? Just be sure. Just to be sure.
Yes, sir.
Okay, thank you very much. So in terms of inertia in power systems, the term inertia is a measure of the kinetic energy in the rotating mass of synchronous generator. So normally you must have heard of inertia before now. So like i.e. the ability of a system which is in motion already to want to continue in motion, or a system that's stationary, reluctant to move more or less. So the larger the system, the larger the inertia, more or less. So if you're just like if you're driving, if you're riding a cycle and you press the brake, immediately the system, the bicycle, the brake will be applied immediately, and the system, your bicycle stops virtually immediately. But if you're driving for example, a truck, for example, when you press the brake, it takes a longer time for the truck to actually come to a stop because of its the larger mass. So it has much greater inertia. Similarly, the same thing applies to a train. The larger, so for a train which is much larger, once you press the brake, it doesn't stop immediately. So the larger the system, the larger the inertia, more or less. It has that reluctance to keep moving, like reluctance to stop while it is in motion, and it also has the reluctance to move when it is stationary. So, and the same that same idea applies in power systems also. So there is a term known as inertia, which is a measure of the kinetic energy in the rotating mass of synchronous generators. Because as you know, for synchronous generators, it's a large, very large mass of rotating of the rotor rotating. It's very massive. It's a massive system. So, and we have the rotor rotating. So, and it has kinetic energy, more or less. So, inertia in power systems refers to the kinetic energy in the rotating mass of the synchronous generators. So, why does this benefit us really? So, the thing is, when you have a disturbance in the system, um, for example, a short circuit or a load imbalance, you get. So, what happens is that this inertia of the system is what reduces the it's first the inertia is what instantaneously responds to these deficits in the power system balance. So like if it's either a load increase or load reduction or whatever the disturbance is, it's the system inertia that instantaneously, so at the instant of the disturbance, the system inertia that goes to the rescue to ensure that the system balance is maintained more or less. It tries to nullify the disturbances or tries to compensate for the disturbances. So it does this by either injecting kinetic energy or by absorbing kinetic energy. So by injecting kinetic energy means the rotating speed of the generator is going to gradually reduce. So gradually reduce, and it's going to injecting this power into the grid. And on the other hand, if it's absorbing, it means the rotating speed is going to increase. So it's going to be absorbing kinetic energy from the grid. So the rotating speed is going to increase, and in that way, it's going to reduce the disturbances in the grid. So some of this concept you may not understand it fully now. You may not understand it fully now, but it will take you more time to grab the concept. So, but nothing to worry. What I just want you to have is a general idea. So what's going on is that what has been observed on the grid is that when they increase the inertia, once they increase the penetration of renewable energy systems. So when you add more renewable energy systems into the grid, for example, you add more wind turbines, you have more solar panels, more solar PVs, which are replacing the conventional generators. Once you do that, so they've observed this in some areas. Okay, they added more renewable energy sources like wind turbines, solar panels, and the like, solar PVs and the like. You realize the inertia was reducing. You realize a decline in inertia. So, and this is representative. This is just representative of what it looks like. So, for when you have high inertia, more or less like the normal level of inertia in the system, when you have generators, you can see that once there's a disturbance in the system, so you can assume this to be the initial condition of the system. You get, so without the frequency deviation. Once there's a disturbance in the system, you can see that when there's high inertia, the deviation is minimal relatively. So it's about maybe 0.5 pu deviation when there's disturbance. But on the other hand, once the inertia becomes low, you get, so as you see, declining inertia. Once the inertia becomes lower, you can see the frequency deviation becomes much larger when there's a disturbance. And meanwhile, the British National Grid stipulates like for the change in frequency by about 1%. So you can see this has already violated that policy. You can see this has already violated that policy. So, and why is this important? Like, you might ask, like, why is this inertia important? Like, why do we have to bother about these deviations and the like? So one aspect is that if you have low inertia, the rate of change of the frequency, you can see the speed that it changes becomes larger. So you have high rate of change of frequency. And when you have high rate of change of frequency, this triggers some protection relays. So there's some protection relays which measure the rate of change of frequency. And they do this to ensure that the system is first is stable and to check if there's no sudden loss of generation. You get, so if there is sudden change in the frequency and you notice that there's a high rate of change of frequency, the protection relays are going to be triggered. So which means once they're triggered, means the system is most likely going to disconnect the renewable energy systems connected at that point, maybe wind turbines or solar panels and the likes. And once you disconnect the renewable energy sources, it's going to create even greater system imbalance. So it's going to be like a ripple effect of problems happening in the system. You've lost your generator. You've lost it if first your relay has been triggered, which was not supposed to trigger, but it triggered because of low inertia. Then you disconnected your renewable energy sources, and then the system imbalance is going to happen more or less. So system inertia is very, very key to maintaining the system stability. We can go on and on, but I want to keep it simple. So going further, so this is one aspect. This is inertia. So as another aspect known as swing equation. So related to inertia. So the swing equation more or less describes the effect of the imbalance between the electromagnetic torque and the mechanical torque on the rotor angle. So don't worry, I won't go deep into this because more or less it's just for you to understand the concept. You can always come back to this presentation later on to understand this better. So what happens is that there's an equation known as swing equation, which is this equation, which describes how changes in the mechanical torque, how it affects the electromagnetic torque, more or less. So, and this is very important because if it gives you an idea of how your system is going to respond when there's a disturbance. How your system is going to respond when there's a disturbance. Yeah, the J here refers to the inertia. You get, the J here refers to the inertia, moment of inertia, J. So, and it's also proportional to what they call inertia constant. This is in per unit, in PU. So J equals to 2H. So this H is inertia constant. So for large generators, so synchronous generators, the inertia constant usually varies from about 2 to 10 seconds. So in some textbooks, you see it as written as megawatts per MVA. So something like that, megawatt seconds per MVA. While in some textbooks, you see it just referred to as in seconds. So inertia constant. So what's key here is so this is more or less a representation of this swing equation. Is a representation. Here you have the mechanical torque. Yes, this synchronization torque, but you can also assume it to be same as the electromagnetic torque. While this is damping torque, which is proportional to this KD omega R. So this is damping gain of the damping gain, more or less. And this is just the what do you call it? The rotor speed, more or less. So anyways, this is just a representation of this. If you want to know more about how this works and the likes, you can refer to this textbook. So I've referenced it here. So but what's key here is that for us to have more converters into the system, so grid forming converters, as I spoke about grid forming converters earlier, we want them to be able to mimic this swing equation. So usually they try to mimic this swing equation so that they can provide a form of inertia, a synthetic inertia or a virtual inertia. So this way, your grid forming converters are also able to provide that inertial, what do you call it, support to the grid to ensure that the grid is stable. So, so that's basically it, more or less. So with the increasing penetration of renewable energy systems, we want our grid forming converters to also have that to be able to provide that inertia, like in synthetic inertia, to maintain the system stability. Okay, going further, another concept known as short circuit level. So it's similar to inertia in one sense. So it's also another issue which is becoming more prevalent with the increase in synchronous generators. Just a second, please. Okay, so short circuit level is basically has to do with the amount of current that flows in a system during a fault. So, and usually for synchronous generators, you can have the short circuit level. So for synchronous generators, you can have a fault current of about 5 to 7 pu of the system's rating. However, for renewable energy sources, you can only have it about 1 pu, and this for good reasons, because for renewable energy systems, you connect them normally through power electronic converters. So power electronic converters, and these converters normally have their limitations. They cannot operate beyond 1 pu really, or maybe 1.2 more or less. So because the electronic converters, the more or less transistors and the likes, and IGBTs and the likes in them have they don't have much tolerance for overcurrent and the likes. So for renewable energy systems, you can only have it at about 1 pu. And what does this cause? So first, when you have low short circuit level, so the protection devices will not operate as expected. So that there will be mal-operation of protection devices. So because normally the protection devices are used to having what do you call it? During a fault that's you have like 5 pu or 7 pu of current flowing during fault. But in the case whereby you have a lot of wind turbines, a lot of solar panels, that means you're going to have maybe 1 pu during fault. How are the protection devices going to know that there's a fault going on? You get, so that becomes a problem, because it's conventional protection devices were designed to trigger a fault once they see the current has gone way beyond 1 pu. They see 3 pu, 4 pu, 5, 6, 7 pu, and they immediately realize, okay, there's a fault. Then they shut down the system, or they isolate the system. But in a case where during fault you're only seeing 1 pu, the protection devices may not work. So this is a problem, because if you look at it, if the protection devices don't work, that means the system continues to operate, and someone might accidentally go there, touch something that is live, and more or less this becomes a danger to life also. So apart from the fact that, okay, apart from the electrical aspect and the other aspect, there's a problem of danger to life to us also. And also beyond that, also we have voltage recovery. So as the short circuit level drops, the recovery of the system becomes much worse when there is a disturbance. So because you're injecting less current during the fault. So, and one thing that is key to note is that the current that is injected during the fault is known as fault current, and it's also proportional to the reactive power, because once the voltage drops, as I said previously, the reactive power is supposed to increase. So during fault, you're expected to have to inject a lot of reactive power as much as possible, or fault current as much as possible, to help with recovery of the voltage after fault. So you can see here, after the fault, the voltage tries to recover. So when the short circuit level is high, the system is able to recover well. But as the short circuit level drops further, you get to a point whereby the recovery becomes oscillatory, and the system, and beyond that, the system becomes is unable to maintain stability. The system goes on, becomes unstable beyond a certain level. So I've given a reference here, so you can something you can read more about later at a later time if you wish to. And so just in the same way I explained for the inertia, something known as inertia constant. For the short circuit level, there's also another component known as short circuit ratio. So short circuit level is proportional to the short circuit ratio. And this is more or less a measure of the system strength. So more or less it's how strong the system is. So usually for the calculation of short circuit ratio, we do, so this is just the formula. So this, you calculate the short circuit level of the system. Previously, I majorly with synchronous generators, and then you divide it by the number of the power from the renewable energy sources. So in this case, so I use just an example more or less. You get, for example, you have the short circuit level was 100 MVA, and then you're adding 20 MVA of renewable energy sources. In this case, your short circuit ratio is about 5. So usually, though these numbers are not cast in stone really, but usually once you have anything below, in some places 3, or in some areas 2, anything below 3 or 2, let me say 2 really, anything below 2, you consider it to be a weak system. So it's considered to be a very weak system. So 5 is actually normal. So it's a normal level. It's a good number. So, but you can just say it's normal level. And when you're getting to like 8, 9, 10, and above, means that the short circuit ratio is that's high short circuit ratio, and also it also means that the system is strong. It's a very strong system. Like I said, the short circuit ratio is an indication of the strength of the system. So once you have an SCR of about 10 and above, you know that yes, this is a very, very strong system. Regardless of whatever disturbances, the system will be able to recover. So, okay. So, going further. Yep. So, getting close to the end. So this is more or less a representation of a renewable energy system. So this could be anything really. It could be from your solar PVs, your wind turbines, wind farms, it could also be an energy storage. And this is just your converter, your more or less DC to AC converter. So DC, and this is AC. So the expectation, from all I've discussed, is that for us to have more renewable energy systems, so more renewable energy systems integrated into the grid, we want them to have some minimum criteria, like some desirable characteristics. So i.e. they should be able to mimic the desirable characteristics of synchronous generators. So one of the things which we look at is the system able to operate on its own? Like, is it able to operate seamlessly when it's connected to the grid? And is it also able to operate seamlessly when it is in islanded mode? So, do you know what islanded mode means? Anyone? So,
no, sir.
So, okay, but anyways, I'll just jump straight into it. So, islanded mode simply means that the system is not connected to the grid. So grid connected means it's connected to the grid. Islanded mode means it's not connected to the grid. It's working, assuming an island. So just take that example of an island that is on its own. So it's islanded mode. So that means the system is working on its own without being connected to the grid. So that's islanded mode of operation. That's a simple definition. So we expect that the system should be able to operate seamlessly in grid connected mode and in islanded mode without any problem. Similarly, we expect our converters to be able to provide dynamic voltage and frequency support. So mainly using droop, that's the droop which I explained earlier, mainly using droop, and also where possible, also implementing some virtual inertia or synthetic inertia. Also, it's expected that our systems should have overcurrent protection. So in your design, the system should have overcurrent protection. So should be able to protect itself when there is faults, more or less. So it should not go beyond, for example, 1 PU for the converters. Similarly, we also expect to have the black start capability. So black start here means that the system can start on its own without any external support. It doesn't need any external support before starting. So it has voltage. It can form a grid by itself without any without requiring any external support. And then it should also have fault right through capability, because as we said earlier, we expect that there will be faults happening in the system. So there could be a fault, a tree falling, anything could go wrong, which is expected. So we want the grid forming converters to be able to ride through the faults without having to disconnect them from the grid. So in conclusion, yeah, this is quite a long one, so but you can all read through. But what's the key take home here is that there's increasing penetration of renewable energy systems. So, and this is due to the socioeconomic factors and energy sustainability. So lots of socioeconomic factors, including climate change and blah blah blah. A whole lot of things happening. So that's why we're having more renewable energy systems being integrated into the grid. And also the conventional control, grid following converters, they do not provide support for the grid. So the conventional controls do not provide support for the grid. And this has led to a decline in the inertia and short circuit levels, and also a reduction in the frequency and voltage support. So hence, for us to have to accommodate more renewable energy systems, these renewable energy systems must actively participate in maintaining the power system stability. And as I said, grid forming converters are the future, more or less. So i.e., we want the converters to be able to mimic the desirable characteristics of synchronous generators. So, and this is important for us to ensure a reliable and stable operation of the future net zero grid. So I think I've come to the end of this presentation, and these are the references. So you guys can always come to this. And one more thing, in conclusion, as I showed earlier, that since we're having more renewable energy systems or renewable energy sources, means that and a lot of countries are driving towards net zero. So i.e. having what do you call it, much more renewable energy sources, and replacing fossil fuels. So that it means that this is the right time for you to do your research or studies, or to specialize in the field of renewable energy systems, so renewable energy systems. And there's going to be lots of job opportunities in the future in this area of renewable energy systems. So there's going to be lots of job opportunities. There's going to be lots of other opportunities for research and the like. So yeah, so I just wanted to chip that in. So thank you all for listening. I think it was really nice having you guys.
Yeah,